disable the electric dry load in Mike Holt's residential load calculator, firstly, go to the calculator, the provided website. Secondly, enter the details of your circuit, such as voltage and current. Thirdly, check the box labeled Exclude Electric Dryer Load. Finally, click Calculate. If you are seeking alternative load calculators that exclude electric dryer load, consider these options. 1. The Southwire Load Calculator is available at the linked website. 2. Electrical Calculator Pro can be found at the provided Google Play Store link. 3. The Easy Electrical Calculator is accessible online. 4. Another option is Electrical Calculations for the Practical Electrician, also found at the provided website. When using these calculators, make sure you have entered all the required information correctly. Double check that the Exclude Electric Dryer Load box is indeed checked. If you continue to experience issues, try using a different web browser or clearing your browser's cache. As a last resort, you can always contact Mike Holt's customer support for assistance. Electrical load calculations are fundamental to ensure the safety and proper functioning of electrical systems. Understanding how to accurately calculate these loads, especially in residential settings, is crucial for electricians, electrical engineers, and even homeowners undertaking electrical projects. The residential load calculator, as exemplified by Mike Holt's tool, simplifies this process by automating the complex calculations required by the National Electrical Code, or NEC. One of the key aspects of residential load calculations is determining the total demand load, which represents the maximum amount of power that an electrical system is expected to draw at any given time. This calculation is essential for selecting the appropriate size of service conductors, overcurrent protection devices, and other electrical equipment. The NEC provides specific guidelines for calculating residential loads, taking into account various factors such as the dwelling square footage, the number and type of appliances, and the diversity of loads. Diversity refers to the fact that not all electrical loads will be operating simultaneously at their maximum capacity. For instance, while a homeowner may have multiple lighting circuits, a range, a water heater, and an air conditioner, it's unlikely that all of these loads will be drawing their full rated current at the same time. The NEC allows for demand factors to be applied to certain loads to account for this diversity. Demand factors are percentages that reduce the calculated load to reflect the realistic maximum demand. For example, the NEC specifies demand factors for ranges, electric clothes dryers, and air conditioning units. When using a residential load calculator, it's important to understand the underlying principles and assumptions that the calculator employs. The calculator typically automates the application of NEC guidelines and demand factors, but it's still crucial to verify that the inputs are accurate and that the calculator is being used correctly. One common source of confusion is the treatment of specific loads, such as electric clothes dryers. As the question highlights, it may be necessary to exclude the dryer load from the calculation in certain scenarios. This might be the case if the dwelling already has a dedicated circuit for the dryer, or if the dryer is powered by an alternative energy source. When using Mike Holt's calculator, the Exclude Electric Dryer Load checkbox provides a convenient way to remove the dryer load from the total demand calculation. However, it's important to understand the implications of this exclusion and to ensure that it is justified by the specific circumstances. In addition to electric clothes dryers, other common residential loads that require careful consideration include lighting, small appliance circuits, general-purpose receptacles, ranges, water heaters, and air conditioning units. Lighting loads are typically calculated based on the dwelling square footage, with the NEC specifying a minimum lighting load per square foot. Small appliance circuits, which serve kitchen countertops and other areas where portable appliances are used, are required to be rated at 20 amps each. General-purpose receptacles, which are used for a variety of electrical devices, are also assigned a specific load value per receptacle. Ranges and water heaters are typically considered to be continuous loads, meaning that they are expected to operate for extended periods of time. As such, they are subject to certain NEC requirements regarding overcurrent protection and conductor sizing. Air conditioning units, which can draw significant amounts of power, are also subject to specific NEC requirements. The NEC provides detailed guidelines for calculating the load of air conditioning units, taking into account the unit's rated current, the starting current, and the power factor. In addition to the individual load calculations, the NEC also specifies requirements for the overall service entrance, which is the point where electrical power enters the dwelling. The service entrance must be sized to handle the total demand load of the dwelling, with adequate capacity for future expansion. The size of the service entrance is determined by the ampacity of the service conductors and the rating of the main overcurrent protection device. When selecting the appropriate size of service conductors, it's important to consider not only the total demand load but also the voltage drop. Voltage drop is the reduction in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can lead to inefficient operation of electrical equipment and can even damage sensitive electronic devices. The NEC provides guidelines for limiting voltage drop in branch circuits and feeders. In addition to the NEC, local electrical codes and utility regulations may also impose specific requirements for residential load calculations. It's important to consult with the local authorities to ensure compliance with all applicable codes and regulations. When using a residential load calculator, it's essential to understand the limitations of the tool and to verify the results. The calculator is only as accurate as the information that is entered into it. It's also important to remember that the calculator is only a tool to assist in the load calculation process. It should not be used as a substitute for sound engineering judgment and a thorough understanding of the NEC. If you are unsure about any aspect of residential load calculations, it's always best to consult with a qualified electrician or electrical engineer. They can provide expert guidance and ensure that your electrical system is safe, reliable, and compliant with all applicable codes and regulations. Understanding electrical calculations extends beyond residential applications. Commercial and industrial electrical systems involve more complex load calculations due to the diversity and scale of equipment. Firstly, consider lighting systems, which are often extensive and require detailed calculations based on the type of fixtures and their energy consumption. Secondly, motors, which are the workhorses of industrial facilities, demand careful consideration of their starting and running currents, as well as their duty cycles. Thirdly, heating, ventilation, and air conditioning or HVAC systems can represent significant electrical loads, requiring accurate assessment of their energy demands. 4. Specialized equipment, such as welding machines, industrial ovens, and data processing equipment, each have unique electrical characteristics that must be accounted for. 5th, power distribution systems in commercial and industrial buildings involve multiple levels of feeders and branch circuits, each requiring separate load calculations. 6. Emergency power systems, such as generators and uninterruptible power supplies or UPS, must be sized to handle critical loads during power outages. 7th, renewable energy sources, such as solar panels and wind turbines, can contribute to the overall electrical supply, requiring integration into the load calculations. The NEC provides detailed guidelines for calculating the loads of commercial and industrial electrical systems, taking into account the diversity of loads, the operating characteristics of equipment, and the specific requirements of different types of occupancies. Demand factors play a crucial role in commercial and industrial load calculations, allowing for reductions in the calculated load based on the probability of simultaneous operation. For example, the NEC specifies demand factors for lighting, receptacles, and motors in various types of occupancies. Understanding the application of these demand factors is essential for optimizing the size of electrical equipment and reducing energy costs. The calculations of conductor sizing are also vital for commercial and industrial electrical systems. Conductors must be sized to carry the calculated load current without exceeding their ampacity rating, which is the maximum current that a conductor can safely carry. The ampacity of a conductor depends on its size, material, insulation type, and installation conditions. The NEC provides tables that specify the ampacity of various types of conductors under different conditions. In addition to ampacity, voltage drop is another important consideration when sizing conductors in commercial and industrial electrical systems. Excessive voltage drop can lead to inefficient operation of equipment, reduced lighting levels, and even equipment failure. The NEC recommends limiting voltage drop to 3% in branch circuits and 5% in feeders. Overcurrent protection devices, such as circuit breakers and fuses, are essential for protecting electrical systems from overloads and short circuits. These devices must be sized to protect the conductors and equipment that they serve. The NEC provides guidelines for selecting the appropriate size of overcurrent protection devices, taking into account the ampacity of the conductors, the starting current of motors, and the interrupting rating of the device. Grounding and bonding are critical for ensuring the safety of electrical systems and protecting against electric shock hazards. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protection devices to trip and to energize the circuit. Bonding connects all metallic parts of the electrical system to create a low impedance path for fault current. The NEC provides detailed requirements for grounding and bonding in commercial and industrial electrical systems. Electrical safety is paramount in any electrical installation, whether it's residential, commercial, or industrial. Firstly, always de-energize circuits before working on them, and verify that they are de-energized using a voltage tester. Secondly, use appropriate personal protective equipment such as gloves, safety glasses, and insulated tools. Thirdly, follow all applicable electrical codes and regulations. Fourth, never work on electrical equipment while standing in water or on a wet surface. Fifth, be aware of the potential hazards of arc flash and arc blast and take appropriate precautions to protect yourself. Sixth, inspect electrical equipment regularly for signs of damage or wear, and replace it if necessary. Seventh, never overload electrical circuits or extension cords. 8. Use ground fault circuit interrupters or GFCIs in wet locations, such as bathrooms and kitchens. 9th, be aware of the location of the main electrical disconnect switch, and know how to turn off the power in an emergency. 10th, if you are not qualified to perform electrical work, hire a licensed electrician. Continuous learning is essential for staying up to date with the latest electrical codes, technologies, and best practices. The electrical industry is constantly evolving, with new products, techniques, and regulations being introduced regularly. Firstly, attend industry conferences and seminars. Secondly, read trade publications and technical journals. Thirdly, take continuing education courses. Fourth, join professional organizations. Fifth, network with other electrical professionals. Sixth, stay informed about changes to the NEC and other applicable codes. Seventh, participate in online forums and discussion groups. Eighth, share your knowledge and experiences with others. Ninth, be open to new ideas and approaches. 10th, never stop learning. Understanding electrical theory is foundational to safe and effective electrical work. Voltage, current, and resistance are the fundamental quantities that govern the flow of electricity in a circuit. Voltage is the electrical potential difference between 2 points measured in volts. Current is the flow of electrical charge measured in amps. Resistance is the opposition to the flow of current measured in ohms. Ohm's law states that voltage is equal to current times resistance, or E equals I times R. This fundamental law is used to calculate voltage, current, and resistance in electrical circuits. Series and parallel circuits are two basic types of electrical circuits. In a series circuit, the components are connected end to end, so that the current flows through each component in turn. In a parallel circuit, the components are connected side by side, so that the current has multiple paths to flow through. The rules for calculating voltage, current, and resistance are different for series and parallel circuits. Power is the rate at which electrical energy is converted into other forms of energy, such as heat, light, or mechanical work. Power is measured in watts. The power consumed by a device is equal to the voltage times the current, or P equals E times I. Electrical energy is measured in kilowatt hours. 1 kilowatt-hour is the amount of energy consumed by a 1000-watt device operating for 1 hour. Understanding how to calculate power and energy is essential for managing energy consumption and reducing electricity costs. Alternating current, or AC, is the type of electricity that is commonly used in homes and businesses. In AC circuits, the voltage and current vary sinusoidally with time. The frequency of AC electricity in the United States is 60 Hz, meaning that the voltage and current complete 60 cycles per second. Direct current, or DC, is the type of electricity that flows in one direction only. Batteries and solar cells produce DC electricity. Electronic devices, such as computers and smartphones, typically operate on DC electricity. Transformers are used to change the voltage of AC electricity. Step-up transformers increase the voltage, while step-down transformers decrease the voltage. Transformers are used in power distribution systems to transmit electricity over long distances at high voltage and then reduce the voltage to a safe level for use in homes and businesses. Motors convert electrical energy into mechanical energy. There are many different types of electric motors, each with its own characteristics and applications. Induction motors are commonly used in industrial applications, while synchronous motors are used in applications that require precise speed control. Capacitors store electrical energy in an electric field. Capacitors are used in electronic circuits to filter noise, smooth out voltage fluctuations, and store energy for later use. Inductors store electrical energy in a magnetic field. Inductors are used in electronic circuits to filter noise, block high-frequency signals, and store energy for later use. Semiconductor devices, such as diodes and transistors, are the building blocks of modern electronic circuits. Diodes allow current to flow in one direction only, while transistors can be used to amplify signals or switch circuits on and off. Programmable logic controllers, or PLC, are used to automate industrial processes. PLC are essentially specialized computers that can be programmed to control machines, robots, and other equipment. Variable frequency drives, or VFD, are used to control the speed of electric motors. VFD can save energy by reducing the speed of motors when they are not needed to run at full speed. Harmonic distortion is a type of electrical pollution that can cause problems in electrical systems. Harmonics are currents and voltages that are multiples of the fundamental frequency of the AC power supply. Harmonics can be generated by nonlinear loads, such as electronic devices and variable frequency drives. Power quality refers to the characteristics of the electrical power supply. Poor power quality can cause problems with electrical equipment and can increase energy costs. Power quality problems include voltage sags, voltage swells, harmonics, and transients. Energy efficiency is the practice of using less energy to perform the same task. There are many ways to improve energy efficiency in electrical systems, such as using energy-efficient lighting, installing variable frequency drives, and reducing standby power consumption. Renewable energy sources, such as solar panels and wind turbines, can be used to generate electricity. Renewable energy sources are sustainable and environmentally friendly. Smart grids are advanced electrical grids that use digital technology to improve efficiency, reliability, and security. Smart grids can monitor energy consumption, detect and respond to outages, and integrate renewable energy sources. Electrical safety is paramount in any electrical work.